mathematics
Yeah,
masters. You know, he always had this dream. He wanted to do mathematics masters. So
yeah,
he
yeah, yeah,
realized his dream. So
yeah. Good for him.
yeah,
Hey, Mr. Lee, try share your slides.
yeah, let me try sharing.
Well, we all have whiteboard behind us. Okay,
Cool.
okay,
Is
because
this okay?
yeah. Can you this one?
Yeah.
Okay, should be okay. Should be okay. You can keep it like this if you want.
Yeah, I think I will keep it just to make sure nothing happens.
Yeah, that
Yeah.
what will happen then?
Then we will spend time trying to fix it.
Okay,
Yeah.
let me check with those who going to live stream in YouTube.
Oh,
Mas Rifki,
oh, this is so shocking.
Mas Rifki,
This,
halo Mas,
so uh, uh, so,
Mas Rifki, kalau YouTube-nya gimana Mas?
Udah Pak, udah jalan
Oh
Pak.
udah, oh oke. We are live, Mas Rifki.
always had this dream. He wanted to do mathematics.
Udah jalan Pak, udah jalan.
Okay,
Oh no, that part. Are we going to save this YouTube?
yeah, try share your slides.
Yeah,
We are live. We are live now in YouTube.
oh,
So we all better well
behave
behave.
ourselves. Yeah. But what we say before
What's that?
is not recorded, right?
We can check since when the live start. I'm not sure.
But
Maybe
it's
it
okay.
will. Maybe the YouTube live will start with what we just say right now.
I think it started with what we said before, but everything is good because
Yeah,
we
it should
didn't
be.
say bad things about anyone.
Yeah, of course.
We are good people and
We
we
are.
only say good things about people.
Definitely, yeah. Hey, Mr. Lee, sorry, because you are at Kyoto, right? So it's like
Yes.
11 something.
Oh, it's 11. It's no
Not yet
problem.
11, right?
Not
Okay.
it's 10:55.
Okay. So later on, you will give talk for 45 minutes to 1 hour, perhaps. And after that,
Uh-huh.
there will be
Okay.
Q&A
Okay.
until here is until 11 a.m. So in Kyoto, will be until 1
Oh,
p.m.
that's quite long.
Yeah. Yeah. So yeah, I just want to apologize. We take your lunch break.
Oh, no, it's no problem.
It's okay.
No problem.
You
Actually,
can have lunch during Q&A for me.
oh,
So,
no. I thought the whole session is 1 hour. So my talk was maybe, I was thinking talk for 30 to 45 minutes and then
okay.
15
Oh,
minutes.
you can talk longer. You
I
can
will talk slowly.
the whole hour to say many things.
I didn't know the Q&A is so long.
Just as much as the audience will. I mean, if there's no more question, then we can call it a day. But it will take your lunch break. You might want
No, there's no
to have lunch
problem.
during Q&A.
No problem.
Okay.
I'm less hungry than the rest of you. You cannot you cannot eat or drink for the whole day.
Yeah.
So
Yeah.
it's no problem for me.
Yeah.
I think maybe audience is more tired.
It's okay. Hari Raya coming soon. Okay. Let's just wait. It's it's still 5 more minutes, so it's still a bit.
Yeah. So they don't join the Zoom online, right? Or they look at YouTube.
Some will join, some will just
Oh,
go to YouTube.
I see.
Because many of us already take our leave.
Yeah,
Yeah. So they may just be on YouTube.
I see. Or maybe they just enjoy their leave.
they look at the YouTube using their phone cell on the phone on the road driving back to their hometown.
No, no, no. I think they should focus on the road.
Also, you are the same lab with Wendy and
Not the same lab, but we are in the same big project.
okay.
It's like
Who's the PI of this project? Your boss, your professor.
PI is the head of his lab. However, his
Okay.
professor is retiring, so I think someone will take over.
Okay.
I think it's another person. This professor is one head, but there's another head. So I think the other head will just continue.
I see.
Yeah.
So this is a very big one. The PI is like
There are many PIs.
okay.
Across different universities.
Okay. Interesting. Oh, by the way, later on, I may need to share your CV. So I think it's okay. Keep it like this, but later on you can close it first and
Actually, it's okay. I will say a bit. I
you
will
can check first.
share a bit myself.
Oh, okay. Then I won't talk too much about you.
Yeah, because they will see this strange guy. Who is this strange guy? Some odd guy from
I will
Japan.
introduce you and you will introduce yourself also. So everybody will know everything.
Yeah, when you are free, you should also come over, and then we will make you give a talk. And this time I will arrange 3-hour talk and 2-hour question.
I can only do the online one. I cannot come to Japan.
I don't know. Maybe there's some funding, but I I cannot speak Japanese, so I am not sure what the structure of all this is.
I thought you speak Japanese already. You're like, don't know, 10 years down there.
No. Two
Three,
and a half 2.5 years.
2.5.
I can only say very simple things.
Okay.
Hello. Thank you. Bye bye.
Okay. Now,
Okay, almost time. Tell me when you wish to start, Mr. Yuda.
it's okay. So we will wait for my boss first, the head of the research center.
Oh, your boss also comes.
Yeah, he will say a bit forward, and then I will sort of opening the session, introduce you a little bit, then you will
Okay.
come in.
Okay.
So let's just wait for him before we start. I don't know why not much people joining us. Mas Rifki, Assalamualaikum, masih Mas Rifki. Halo Mas.
Iya Pak ya.
Memang belum ada yang join ya Mas ya?
Di YouTube sih udah ada Pak.
Oh, yang di Zoom
Zoom belum ada yang masuk
belum ada
lagi.
ya? Oh, bukan lagi nunggu di apa di luar
Enggak
gitu.
ada. Enggak ada. Ini
Oke.
langsung masuk.
Oke. Okay. Maybe everybody is on leave now. Let's just wait a little bit. Just wait for Pak Sulaiman. Jesus. Sulaiman. Okay.
Thank you.
Hmm. Okay.
Hello, good morning.
Good morning, Pak Sulaiman.
Morning.
So Shawi is already here, and now it's already 9 a.m. 2 minutes from 9 a.m. Maybe we can start the colloquium probably, Pak Sulaiman.
Okay.
So okay, yeah, many of us probably watching this in YouTube, and people come to Zoom one by one. Maybe we should just start.
Okay. Yeah.
Yeah. Okay. Good morning, ladies and gentlemen, friends and colleagues, everyone. My name is Yuda. I am the senior scientist in Research Center for Climate and Atmosfer under the National Research and Innovation Agency. So today we will have a seminar series. We call it PRIMA Kolokium. And before we start, as the opening for today's activity, maybe our head of research center, Pak Sulaiman, perhaps some word from Pak Sulaiman.
Okay. Terima kasih. Good morning, ladies and gentlemen. Thank you first. We appreciate thank you very much for Dr. Lee for your willingness to give some lecture related to the climate simulation for extreme rainfall. Yeah. In Indonesia, we get some extreme rainfall, so the simulation of the extreme rainfall is very important. We also some research related to the extreme weather. Many researchers in our research center also interested in weather, extreme weather. So in the next, maybe we can some discussion and maybe make some collaboration. Yeah, I saw you also collaborate with Sun Yat-sen University. So I have friend in Sun Yat-sen. The name is Professor Wei Dong Yu or Wei Dong
Yes,
Wu.
very famous.
Yeah, it's very famous MGO guys. Okay, thank you very much. Saya kembalikan ke Pak Yuda.
Yeah, thank you, Pak Sulaiman. Okay, as we all see in the screen now, today's talk is very special. We will hear talk about climate simulation of extreme rainfall. The speaker is Li Xiaoyi, Dr. Li Xiaoyi. Maybe I'll just give a quick introduction about him. Dr. Li, maybe I will share your CV. Just a quick look on your CV. You can switch off your screen first.
Okay.
Okay, just a quick introduction about Dr. Li Xiaoyi. So he did his undergrad in Caltech, that's in the States, and then he did his doctorate degree in NTU, and I was there also last time. So we're actually a lab mate actually. So after he did his graduate degree, Dr. Lee have a lot of experience working in several institutions, doing postdoc in Sensem, in Smart, and US a couple of years, and joining the Singapore Met Office for a couple of years. And then in 2017, become a faculty in Sun Yat-sen University in China for several years until 2021. Back to Singapore until 2022, and then from 2022 until right now, he is a researcher in Disaster Prevention Research Institute, DPRI, Kyoto University in Japan. And regarding publication, he is involved in many peer-reviewed publication, like the one he has with Xiong Huang from MIT, and then published with John Bright, he's an Australian meteorologist, and so on. So today the talk will be on his work in Japan on simulating extreme climate. So Dr. Lee is already here. You can see he's already with us. So Dr. Lee, you have 45 minutes to 1 hour to give your talk, and then we can use the rest of the time until 11 a.m. here in Indonesia for Q&A. So please join us welcoming Dr. Lee. Go ahead, please, Dr. Lee.
Okay, I'll share my screen. Back to this. Okay, I think, can you see my screen?
Yes.
Okay, so Yuda, my friend Yuda has already sort of gone too much into the CV, but maybe I can tell you a bit of what type of research I have been doing in the past. So I was doing my PhD with Professor Ko in the same lab as Mr. Yuda, Dr. Yuda, and then it was on Hadley circulation, but it's analyzing reanalysis. I started learning how to do climate modeling with Dr. Wang. And then I went to Meteorological Service. The Met Service did 2 national climate change studies where we did future climate projections for Singapore, mainly Singapore, a bit on the surrounding areas. And there were 2 versions of it. There were the version 2 was done in collaboration with the British scientists at the UK Met Office, and then version 3 mainly done by ourselves with some help from BOM in Australia. And in between, I went to China, and we were in a team helping to set up some marine forecast system over the South China Sea. And now I'm in Japan, and I'm working, I think, at the bottom, you can see the logo, bottom left. It's the MAX program, the Japan Ministry of Education research program, also for studying climate change. It's a very big project. So I will also show the results from some Indonesian colleagues in the same project. There are many people. Okay, so after doing so many climate change study projects, there are some questions that are in my mind that I start to think about. So the first thing is, what is the meaning of a climate projection? So as you know, we need 30 years to be a climate, right? According to WMO. And when you do statistics, you take 30 samples, 30 years, it means that you're growing from the same population. So this applies to past climate where it's not warming. But in recent years, the climate is already warming. You can see from the IPCC report picture, even in the 1990s, 1980s, it started warming already. And faster and faster in the future. So we can sample and call it a climate in the past. But if your climate is warming, how do you call it a climate? What does the meaning of climate projection mean when you run a future simulation? You take 30 years or even 20 years, 40 years, and you do some statistics. So this is a bit troubling to my mind from a mathematical standpoint. Second point is there are these things where we do this multi-model mean, because each global climate model, GCM, have their own bias. So what is prescribed in these climate projection simulations is the emission. So it's given greenhouse gas emission or aerosol emission, and then the model, the GCM, will produce a response. But different GCM will produce a different response. So some groups of GCMs are the so-called warm models. So they warm a lot. And there are some GCMs that are the cool models, and they don't warm a lot. So the idea is, if you average across many GCMs, you have a good idea, sort of good estimate or good uncertainty estimate of what the future may look like. But again, from a statistical point of view, each GCM will actually have its own climate. So what is the meaning of climate? Is it a 2-degree warming climate? Is it a 1.5-degree warming climate? So these are some thoughts that I start to think about that trouble me slightly. So with this in mind, I would like to share the program I'm working on and how they structure their climate projection. So more details can be found in the reference, but you can see that the historical climate, as I said earlier, is pretty stable, and then it already start to warm a bit. So these historical experiments run in GCMs, they are not exactly a non-warming climate. They are already a somewhat warming climate. So in our experiment done by this research project I'm in, first they try to remove this warming trend. So they have artificial, sort of a hypothetical situation where there's no anthropogenic warming. So this is a natural run. And after they do the natural run, they then scale upwards from natural run. The first version is 4K warming, but they have also run a 2K warming. 4K is a bit high. So 2K is more, around 2K is more like what is projected. At least we hope it will not become 4K, right? So then how they implement this is they look at CMIP and they look at the SST change patterns in the future. And then they sort of take a couple of representative SST changes, because although there are many models in CMIP, some of them belong to the same family of models, so they have a common ancestor. And so due to their similarity, their change is actually quite similar. So some groups of representative SST changes can be detected from so many models. And then these SST changes are all scaled to be uniformly 4K. So this means that when you take a multimodal mean climate, in the sense that it's a multimodal SST change, all of these are 4K, so it's standardized. And then you can, I would say, sort of make better sense of what kind of response you are getting from, because you have standardized all the warming to 4K or 2K. So I will go back to this a little bit later. I would also talk about my other questions about this climate projection. So the simpler form of climate projection is you have some GCM simulations, for example, from CMIP 5 or CMIP 6. And then you have some of your local historical observations from stations, rain gauges, or maybe more modern radar. And you can try to have some statistical rules to convert the historical simulation results of the GCM to your local historical observations. And then you run your future simulations, and then you apply the same rule, assuming that this rule will not change. And from this, you get your local future projections. So one issue with this method is that GCM resolution is much coarser than your society scale. Society scale means human scale. We care about whether our city is warming, whether some farms are going to get drought, or some part of the country is going to be flooded. So these scales, for example, recently we have a lot of extreme rainfall. It's not extreme rainfall over whole Indonesia, right? It's extreme rainfall over Bandung, small area. So it's small area for the GCM, but it is big area for human. And GCM resolution has been improving. Long ago, maybe 2 degrees. Now in CMIP 6, there's this experiment set called high-res MIP. It is around between 0.5 degree to 1 degree, so about 50 kilometers to 100 kilometers. And of this model, I can see that the highest resolution ones are EC Earth and Head Gem. And these are about 4 degrees, so or 3.35. So maybe 35 kilometers to 40 kilometers. But still, this is a bit coarser than what we really care about. So the other method, which is slightly more complicated, but tends to give better results, is, well, you have many of your GCMs again. And from CMIP, there are more than 40, right? So you can't handle all of them with this method. You can select a few, maybe ones that you think are representative, like certain families of GCMs. You can select one from each family, or you can first analyze them to find out which ones reproduce your local climate best. Then you use your regional climate model and you downscale them. And for example, Codex experiment. So you can also have different regional models or different ensembles of the global climate models. So after you have downscaled through your regional climate model, again, you have your conversion rule. So in this case, I would consider it more of a bias correction, because generally the regional climate models produce results that are more similar to the observations. So, and then not to repeat, you will do your future simulations and you get your future projection again. So after looking at quite a lot of GCMs and RCM results, I have some doubts in my mind. So some phenomena are not simulated in the GCM, or they are simulated, but they are not very well simulated, not realistic. So since the RCM is driven by the GCM, are we so sure that the GCM, what is not simulated in the GCM, so it doesn't even exist in the GCM, or not in the form that we can recognize it as? If it's not in the GCM, can the RCM then produce it? Because the RCM is driven by the GCM. So second question is, we do believe RCM can simulate better results, and it has been shown by many studies. But is what we have high resolution enough? Human resolution is very high. If your house is flooded, you care about something that is tens of meters, right? Your neighborhood, your fields, your buildings, all these humans care about very, very high resolution things. Extreme, not talking about extreme rain, maybe talking about extreme wind. Extreme wind, you care about the damage to very small scale, tens of meters. Your trees being ripped down or broken by extreme wind is also very, very fine scale. So is the RCM even high resolution enough? And the third one is not so much scientific, but it's very technical and it's a very realistic problem. All this is very computationally expensive. So I think these climate projections and related climate experiments, it should be available for everyone to do research on, to carry out, because different people from different regions, they have their own interests and their scientific questions. So it cannot be just so easily derived from a general simulation like CMIP. So you may wish to do some perturbations that address questions you are interested to. So how can we make this climate simulation accessible to everyone? That means everyone can do it. So these are the important questions. And I hope to try to give some ideas in this presentation. So going back first to the first question about simulation and resolution. So the experiment I was talking about is actually called D4PDF. So database for policy making future climate change. And we want higher resolution. So it starts from a 60-kilometer global climate model run by the Meteorological Institute of Japan. The name of the GCM is MRIAGCM, the atmospheric only model. And then it gets downscaled to 20 kilometer. So over this region, so this is Japan, Korea, China, and then furthermore, there's a further downscaling to 5 kilometer, but now over a smaller area. So another thing about this downscaling is it's so expensive that if you have the money to do it, you can only still do it for a limited area, your own region. So is there some way that everyone can benefit from higher resolution? That's the question, right? But first we have to see, is this resolution enough to reproduce the type of extreme rainfall that we want? So before that, because I did the verification for Japan only, I would like to share the results of some Indonesian scientists in the same big project, but they have been carrying out some comparison and verification of this default PDF dataset over a maritime continent. So Dr. Wendy Abjupa, also from the same organization, maybe he's listening in, I don't know. But so he has been studying AGCMs, right from CIMIC, and then comparing D4 PDF and AGCM, and he's looking at cloud water content, comparing with TRIM, satellite, AGCM, and D4 PDF. And he finds that D4 PDF and AGCM do show comparable results, and they are able to produce this increase of cloud water content. And you can see that on the left column is the past experiment, and then on the right column is the future projection. So projected, it seems to increase. And then he also shows some trend, and you can see TRIM. Unfortunately, TRIM is not a very long period, but all the models do show some comparable results, showing increasing trend. So seems like it will be more risky in terms of extreme rainfall in the future. And then some other project by the same research group as me, Mr. Novria Sagita from BMKG. So he is studying NHRCM. NHRCM is the Japanese regional climate model. So same regional model as used in D4 PDF. And he's studying thunderstorm environment. So thunderstorm environment, it's very hard to predict the thunder, right, or the thunderstorm, but you can sort of analyze the stability of the atmosphere. So he defined thunderstorm days as when the vertical wind shear is greater than 0, but and then and 10 knots, and then the cape is high. So and he also compared the model on the left side with the right side, which is observation based, the Earth Global Lightning Network. And then he find that the model can actually produce rather comparable results. So in different regions, the seasonal pattern of the thunderstorm days is similar, but the model actually slightly overproduced. But this slightly overproduced can probably be bias corrected, I think. And then he also analyzed how this will change in the future. And it seems that it will actually depend on the region. So some regions, there are more moderate thunderstorm days. So region A, red color, and region C, the blue color. But for region B in green color, is doesn't increase. Maybe it decrease, right? So I'm not so familiar with the geography, but it seems somewhat geography related. Okay, back to Japan then. So those were sort of rainfall related parameters, but now I directly compare the hourly extreme rainfall for Japan. And this is a bit of a complicated plot, so I have to explain. So as I said earlier, there are 3 resolutions, right? I would like to see which resolution is enough. So gray color is the 60 kilometer GCM, and you can see some shading because it's an ensemble run. So the ensemble has a envelope, a range, and blue is the 20 kilometer, and then green is the 5 kilometer. 20 kilometer and 5 kilometer are the RCMs. And the x-axis is the upper percentile rainfall, so 99 percentile, 99.9 percentile rainfall that I calculate for summer rainfall, June, July, and August. And then the ensemble range here, what percentile? So y-axis is the rainfall amount, millimeter per hour. Then all the thick black lines are radar. And then the gauge is in dotted black line and solid red line. So why is this so? So the simulation period is 1952 to 2010. Unfortunately, the radar is only from 2006 to 2022. So they do not really overlap, maybe only for a few years, around 5 years, right? So when you compare them, it's not an exact comparison. So we supplement with rain gauge also. And rain gauge, the long period rain gauge in red is the same time period as the model. However, we also put a short period for the rain gauge, same as the radar, to see how the rain gauge extreme rainfall changes depending on the period. So in general, I think you would just try to see which envelope will match best with all the observation-based data. The observation-based data are the thick black line, the dotted line, and the red line. So they also give you some example of the kind of values that will come from observation. So actually, I did for all the individual regions, but I cannot show all, and you will not want to see all. It's too boring, right? And so I selected a few areas, which are areas where there are major cities. So most of the population is there. So I think most famous is Tokyo, right? The capital. And you can see the 60 kilometer cannot produce proper extreme rainfall. It's very weak. Actually, for all regions, it's not very good. And then the 20 kilometer is better. So it does seem better. In some areas, it is actually quite comparable to the observation. But in other areas, for example here, it's not so well. And then we have 5 kilometer rainfall in green. So it seems to me better than the 20 kilometer. So in some cases, for example, you see Tokyo, actually the 5 kilometer may be overproducing. So for 99.99 percentile, but this is very extreme. So usually, I think you will not really believe this values because there are very few samples. So for 99.9 percentile or 99 percentile, you can see the green does match the rain gauge quite well. You can see the 99.99 percentile is like 80 millimeter per hour. That is like maybe one time in history, something like that. So it's not very robust in a statistical sense. So if we look at what we think as extreme rainfall, maybe 40 millimeter per hour, yeah, I think the 5 kilometer model can reproduce the observation. So if we have a high enough resolution regional model, so I believe, yes, we can reproduce the extreme rainfall climate statistics. So of course, also for river basin, all these are the river basins, but if you look at the river basins, yeah, the 5 kilometer actually does very well. So I have to say something about the plots I show so I don't mislead you. Actually, I have done some scaling of the extreme rainfall. As we know, for average rainfall, when we calculate mean rainfall or total rainfall, the value we get for different spatial resolution is different. So we have to do conservative scaling to make sure total rainfall is the same. But the value that if we just calculate straight away, it may not be the same, right? So this is also the same for extreme rainfall. And this is very intuitive. So if you have one extreme thunderstorm at 20 kilometer, and it's just one thunderstorm, but the outside is not having this extreme thunderstorm, and then you calculate the extreme at 20 kilometer, you get this thunderstorm extreme rainfall. Then when you average this rainfall to maybe 60 kilometer resolution, so your time of the thunderstorm will be averaged over 9 grids, right? So one extreme rainfall grid and then 8 other non-extreme rainfall grid. And this value will be weakened. And if you then take this data set and you calculate your 90 percentile, 99 percentile, your extreme value will also be weak. So we have to scale it. So how I did this was radar has very good spatial coverage. So I take the 1 kilometer radar rainfall, and then I regrid it to the same resolution as the simulation. So 1 kilometer to 5 kilometer, 1 kilometer to 20 kilometer, 1 kilometer to 60 kilometer. And then for the same data set, I calculate the percentile. And then you can see this is so actually based on some extreme statistics. The extreme can actually be scaled by a linear factor. So we can just multiply by a scaling factor. And after I calculate the scaling factor from the radar, I will apply the scaling factor to the extreme values I calculated from the model. So all these I show are scaled to the same resolution. Only when you scale to the same resolution, it is a comparable, so they are fair, right? So the comparison is fair. But for the 5 kilometer extreme rainfall, the scaling factor is very close to 1. So actually, if you use the 5 kilometer, you don't need to scale, because I think the scaling factor is within the uncertainty of the ensemble already. So you can use as it is. And Then now we have the extreme rainfall. We also want to do some kind of estimate. How has the extreme rainfall changed? How much more probable it has changed? So in this, we can use the non-warming simulation, and we can also use the warming simulation, and you can show their uncertainty, right? And so in this case, right, you can see, yeah, maybe it's not so easy to see because it's quite small, but actually the envelopes are separated by the confidence interval. So these hourly extremes have increased, so it's statistically significant. But for daily extremes, the envelopes overlap too much, so it's not significant, so no change. And you can calculate the exceedance probability. So take your non-warming scenario. So you have this upper percentile, say exceedance by 0.1%, then you can get a rainfall threshold. Then you apply this threshold, you search for the historical simulation, and you can then compare how probable this extreme rainfall threshold is reached. Yeah. So then you can do it for different regions, but I don't want to go into that because you won't find it too interesting. But we will also test for robust signal. So for each percentile, we try to check it. We want something that looks like this. We don't want something that looks like this or looks like this. Okay, although in this case, it seems like this is just a bit depending on how you want to cut it, right? But generally, we want a tail that's quite clearly above, or in this case. And then, not going into the right, I think you can look at the left side. So we know that hourly extreme rainfall will increase, but you can see that in actual fact, the model does show some regions where the signal is not so strong. And then it becomes much clearer in the future. So this is historical, and this is future. And then for daily, the signal is a bit mixed. So some areas, actually, the extreme rainfall is less probable. But in the future, it gets warmer all over. So I think some Japanese scientists I discussed this with say it's probably some kind of a topological effect, or region by region. Some areas are more protected by mountains. Yeah. So I just want to go on to the next question. So tropical cyclone simulation. As we know, of course, tropical cyclones need to be resolved, and higher resolution is better. First reason, even over the ocean, they need high enough resolution to reach the proper intensity. And then nearer the coast, depending on what kind of topography they pass through, they can be weakened by the topography. And of course, people are interested in where they make landfall. But it's very expensive to run high resolution GCM because the tropical cyclone starts over the Pacific Ocean. So it's very big for regional climate model. So, and then tropical cyclones don't come all the time. They are short events. So if you then have a GCM and downscale the whole period, 30 years, it's very expensive also. So is it possible, my proposal is this, if we can find the tropical cyclone in the GCM first, and then individual case of tropical cyclone, we will downscale it. But the problem is the GCM is coarse resolution, right? So can you actually have a tropical cyclone or good tropical cyclone in the GCM? So we decide to do an experiment on this using the community of system model. This is not a new model. It's been around for many years. And we are using the newest version, CSM2. And the interesting thing about this CSM2 is that it has an option for regional nesting, variable resolution. So this is a global model, but it can sort of act like a regional model with finer resolution over your interest or region of interest. So there are two grids available in CSM2. This is over Arctic, this is over USA, because this is a model developed by Americans, so they are very interested in this area. And of course, this area is quite a complex region, so they are also interested in it. So what to do? We decided to build our own mesh for Pacific. Asia Pacific is actually in the default mesh over this junction of this multiple mesh. So this is not good for simulation because you can have some edge effects or some propagation effects. So first we make it higher resolution, then we rotated the grid, and then for this region of interest, we start shrinking it. Yeah, actually, I was sort of more interested in the lower bit. So, but we were funded by people who are interested in this part. And of course, for tropical cyclone, they tend to go like this. I think if you are interested, you could actually build one central over here, right? Okay, so after we do the climate simulation, and then we have some algorithm to find the typhoon tracks, but I will not go into this. But the GCM also has a problem. The output, we can make it into 6-hourly output. Originally, GCM output is monthly, right? Or even daily at most, but you can put it to quite high resolution temporarily, and you can find the tracks. But actually, typhoons are classified by their maximum sustained wind. So it's a gust wind, right? And again, we have to do something similar to the rainfall scaling. We also have to scale it. So in this case, we compare IB tracks, which is the observation, and ERA 5 at different regraded resolutions. And again, we calculate the scaling factor, and then we scale the winds, and then we calculate the typhoon statistic. So the scaling factor is about 1.7 to 1.9 from 6-hourly mean wind to the 10-minute gust wind. And IB tracks is the observation, ERA 5 is the reanalysis. So you can see from here, there may be some over prediction, but the total system is pretty similar, and you can get some super typhoons. So these are the most intense typhoons. And now we have this scaling factor. We try to apply this to our model. So this is the observed tracks and their intensity. This is the 1 degree resolution, and this is the 0.25 degree resolution. So you can see from this line, this is the result from the 1 degree. The 1 degree cannot really produce typhoons. So the systems are all too weak. They tend to look like depression. And it gets better at 0.5 degrees and only at 0.25. you get similar number of tropical cyclones as observation. Similarly, if you look at the super typhoon, most intense systems, you cannot produce enough. You don't produce any at 1 degree. You produce some at 5.5 degree. But at 0.25 degree, you get similar to observation IB tracks. So we conclude that the 0.25 degree is a good resolution for our GCM. And as it is only locally high resolution, like opposite side of the Earth, we are not interested. Actually, we save a lot of computation resource this way. This is an example. So sea level pressure, wind speed, and rainfall. 1 degree, very weak. 0.5 better. So 0.25, you can really see the intense wind, and you can see this structure and the comma-shaped rainfall and the rainfall band coming out. So at 0.25 degrees, this is on the upper end of regional climate model. So if you start from the 0.25 degree GCM output, you can, I think, I haven't done it yet, but I think it's a good way to go smoothly into a regional climate model and produce a properly strong tropical cyclone. Okay, so last part. So we have been talking about atmospheric model, but what about ocean models? Actually, earlier I said Arctic is a very complicated place. But the other second complicated place for ocean circulation is a maritime continent. So Indonesian through flow and the South China Sea through flow, Indonesian through flow over here at the Mindanao, and South China Sea through flow over here, they actually play important roles in the global heat exchange. So can we have enough resolution for ocean models to capture the proper climate? Okay, this is a zoom in, right? And you can see the flow is very complicated. I think many of you will know this better than me. So I will not embarrass myself by making some mistake about oceanography, but it is very complicated, and the coastline is very complex. So we need a high resolution ocean model. So we meet the same problem as the atmospheric model. Actually, one of my colleagues tried this experiment with a variable resolution ocean model. The model they use is called FVCOM, I think. This is a sort of a advertisement for them. And they have verified it against observation data. And later on, in this Southern Marine Science and Engineering Laboratory, they have extended it to a global model. So they fit this model into a global model, global ocean model. So if you are interested, you can contact Dr. Shi to ask him more about his model. And my summary is this. Okay, I think from testing for myself and doing the verification for myself, I am convinced that yes, that our hourly rainfall extreme can be accurately simulated by a high resolution regional model. Of course, the model must be suitable for the region. So that's why I showed you the results for Indonesia. But those are convection and storm related statistics. So I don't know for the rainfall itself. And then my second proposal is maybe we can save computational costs by finding the extreme events in the global model first, and then we simulate these extreme events So the times where there are no extreme events, we don't need to simulate. We don't need to downscale and waste our computation resources. And then thirdly, another proposal is to control the computation cost for doing the global models. There are global models with variable resolution, so they can zoom in to the target region and produce better event statistics at reasonable cost, computation cost, and then these better events will exist in the global model, and you can then downscale them further to much higher resolution to get even better statistics. So I think it's exactly 1 hour. So thank you very much. Terima kasih.
Thank you, Dr. Lee. Wow, it's a lot of materials to digest right now. And now it's 9:56 in Indonesian time, and we have maybe 1 hour, a bit, 5 minutes more probably. Now it's Q&A time, and as usual, I will start with myself asking a question. And I actually have plenty of questions, Dr. Lee, and maybe I have one first. So you use the 4K and 2K scenarios for the Japan extreme rainfall project. I'm just curious why. I mean, maybe you have explained it, but we understand that for the future projection, you have the greenhouse scenario, the RCP and SSB. Will you also do for those scenario as well, or is there any reason you start with this 2K and 4K instead of those RCPs?
Yeah, I didn't design the project, so I'm not exactly sure why is 4K. I think it is an upper bound, but now we know it is maybe too high, and therefore people using the data set requested for a more realistic warming value. So after the 4K and they found it's a bit extreme, they then did the 2K. And another reason why I would say, speaking for myself, why I would use a 4K instead of a more realistic, maybe 2K or 1.5K or 1K. There's a lot of internal variability in the climate models. So when you try to detect a climate change signal, it's more clear to detect it when you have a lot of warming. So you have a very strong warming, and then you are confident that it does cause a change impact. Then after you know that it does cause a change, you can go back to a realistic value, maybe 1.5K or 2K, and then you calculate again to find the weaker value. Whereas if you start from 2K, if for myself and I see something, oh, it's not statistically significant, I'm not sure, then I will have a lot of doubt about my result. Should I say there is impact, or should I say there is no impact? I will, as a scientist, I will say, I don't know. It's not significant. So I think for myself, this is one kind of a theoretical experiment I will do. Make a very strong result first, then scale to the repeat for realistic when I'm sure there's an impact.
I see. So it's a good start, good choice to start global warming scenario experiments, so-called with the 4K, I guess. Okay, thank you for
RCP 8.5. Yeah, it's
8.5,
RCP
yeah.
8.5 is also the most extreme case.
Right,
But
right.
yeah, maybe very extreme. Yeah.
All right. Thank you so much for the answer, Mr. Lee. Maybe we give to the floor, so you may raise your hand or just directly open your mic to ask question to Dr. Lee. Haven't seen any.
By the way,
Okay,
I see
maybe
Dr.
I have
Wendy is
another
here
question.
too. You can also direct questions to him regarding his
okay.
results, because he analyzed
Right.
clearly over Indonesia.
Right. Yeah, so
Hello,
maybe question for Wendy also.
Pak Pak Yuda, izin.
Halo Pak Wendy.
Halo Pak, salam kenal. Baru pertama kali ketemu kayak.
Iya. 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 Jadi kalau mau tanya Pak Wendy juga bisa ya, terkait apa verifikasi tadi ya.
Iya,
Okay, we
siap.
have one. Okay, Ardi raise his. Okay, go ahead, please, Ardi.
Hello, can you hear my
Ardi?
voice? Can you hear my voice?
Yes.
Okay. Thank you,
Yeah.
Dr. Lee, for
Go ahead.
your excellent presentation. So actually, I also work with model, but currently I'm working more with the numerical model other than the GCM. So I'm interested with your results about the verification of hourly extreme rainfall in Japan. So I saw that you didn't use same ensemble members for each resolution. For example, like 60 kilometers, 20 kilometers, and 5 kilometers. So is it because the computational restrictions or other factors? Because I think if you use the higher resolutions, like for example 5 kilometers, there will be more chaotic results. But I saw that for 5 kilometers, you only use like a fewer ensemble members compared to the 60 kilometers. So that's my question. Thank you.
Yes.
Thank you, Ardi. Go ahead.
Thank you.
Dr.
Yes, I understand what you mean, and this was my concern also. But these are all the available ensemble members. So global model has 100 members, but they only downscale 50 to 20 kilometers, and then they only downscale 12 to 5 kilometers because I think it's too expensive to downscale 100 to 5 kilometers. I have also done the comparison for the same 12 ensemble members. So global 12, 25, all the same 12 ensemble members. The qualitative result is not changed. I think you can see the chaoticness because in the 5 kilometer, the envelope is wider.
Yes.
So yeah, so even with the 12 ensemble members, it is pretty similar actually. I would like to see everything downscaled, but I think it's too expensive. So this is a technical limitation.
Okay, I got it. And the second question for Dr. Wendy.
Apa Mas?
Wendy-san, I would like to ask, have you tried to use another data sets? I see that you used the TRIM satellites data set for your simulation. So have you considered a longer observation for your simulation to project the extreme rainfall in Indonesia? Thank you.
Yap. Ini langsung dijawab aja ya Pak Yuda ya.
Yes. Please go on.
Thank you very much, Mas Adi. Long time no see you. Maybe more than 10 years. Yeah, Pak Yuda, Dr. Lee, Mr. Adi, Dr. Adi is my very long how to say, old friends, maybe 20 years ago. We have collaboration with Japanese. Yeah, Dr. Adi, Dr. Ardi. Yeah, about the plants, of course, I think as maybe we know all that the extreme rainfall is increasing. Then we can, recently we have big flood in Jakarta. Maybe at least since 2020, we found many big floods around Jakarta and other places. So I think this is maybe my reason to use the model data. The model data, because as you know, Dr. Hadi, I'm not a model person. I mean, I never used model before, right? The observations, there are observations, and then I got the project by Sentan with Dr. Lee. Then I used from the beginning, I do research about the warm cloud, warm rain in Jakarta region, as already shown by the Dr. Lee. But of course, in the future, it is very interesting to use the longer period to validate the model data. Because, I think I heard that also BMKG now use the Cordex. I think this is collaboration project with BMKG and Malaysian, Dr. Tanggang, Professor Tanggang, and maybe also Dr. Yuda also, I think now been collaborating with them. But that's why I think very interesting. One problem that I found now, if we use the atmospheric or P level data, the resolution is very coarse. Even the GCM model provide us maybe around 60 for the global, but it is for surface, not for the upper level. For upper level, GMA just provide 1.25 degree for the P level data. So this is, this our trouble. And now, as already shown also by the Dr. Lee, we have like NHRCM. This is more nice, more fine resolution for the P level. Already, our colleagues from BNKG use it, and also I have also the data, and of course I wish to use it, but the problem is the NHRCM data is not so good. I think in the producing, right, Dr. Lee, maybe I'm not sure you know about it, but the time is not so good. And yes, come back for your question. I plan to use like for the surface, Dr. Adi. Maybe I will use the Emerge or a GS map, and GS map now already accommodate the like orographic effect. Then I think it is good for us to validate the model data, whether they can use like an RCF or Cordex, whether they can use capture also the orographic. Then if we can validate it, then we can solve like to give the input the like hydraulic model that maybe can solve also can give the how to say it much more information for the flooding in Jakarta, which is whether it's like very downstream area. So maybe I think that's all. It's too much, I think, because long time to talk to you. So that's
Okay,
all.
okay, thank you very much.
You're welcome. You're much welcome. That's all, Pak Ida.
Hey,
Dr. Lee.
yeah, thank you, Adi and Pak Wendy. I think I'm not sure if Dr. Lee monitor the YouTube. They said there's some question down there. Let me try to see the question.
Let me try to.
There's a question in YouTube.
Let me.
Or if there's any other, you can also. Let me check what's in YouTube.
What's on YouTube?
Maybe during waiting for that question, can I have some question to Dr. Lee, Pak Iwan?
Yeah, please go ahead. Go ahead.
Yes, please.
Yes, yeah, I think we know that we have now some model data for Indonesian regions. So then my question, Dr. Lee, I think this is a basic question, how we can accommodate all of the data, how to combine all the data to solve I think there are maybe not only the hydrometeorological purpose, but also maybe for bigger image that for the water cycle in the South Asian country like Indonesia, Singapore as well. So I want to hear your perspective about it, because I think this is very important for the future, since we got many problems with this. Not only, of course, the hydrometeorological disaster, also maybe other purpose to use the model. Thank you, Dr.
Yeah, this is a problem that we have faced for forever. This is because each people of atmosphere people, ocean people, hydrological people, land people, we all have our own style, our own terminology, and it's very hard to work with each other. As I said earlier, I was working with the oceanographers in China doing the marine forecast model, and even atmosphere and ocean, which are so related, it was so difficult to work with them. For example, our wind direction, we say northeast wind come from northeast, southwest wind comes from southwest. But when they say northeast current, they mean the current going to the northeast. And southwest current is current going to southwest. So we could talk about our shortwave flux and long wave flux, and we have a convention, right? Downward or upward, or this. Theirs is opposite. So because for them, the shortwave flux is going into the ocean, but for us, the shortwave flux coming from sun going down. So even the sign or direction is so different. It's very hard to work. I have no solution for this. This problem has always been existing. Sorry. Very difficult.
Yeah, thank you, Dr. Lee. This is our homework as a researcher in this.
Yes,
in
we
this
have
field.
to try.
Yeah. Yes.
Okay,
Yeah.
thank you, Pak Wendy.
Yeah.
Maybe
Sama-sama, Pak Iwan.
we can move on to one question in the chat box. Dr. Lee, maybe you can see the chat box. There's one question. It comes from YouTube, so you can open the chat box in Zoom.
Live chat.
Did you see the chat box? So there's a question there, or should I just read the
Somehow I cannot scroll down. Let me
Okay, it's
try.
okay. I'll read it for you.
Why a coarse resolution simulation cannot show extreme rainfall? Grid averaging effect, yes, that is true, but there is a real physical reason behind this, because if for extreme rainfall, you usually have a small spatial resolution. The phenomena also is like one convective plume going up, so it's a thunderstorm, and then if you have seen this type of thing happening before, it is so it will go up and psh. So this actually cause a lot of short short period extreme rainfall that caused a small area flood, but it's very bad for the people there because very hard to forecast, and it will happen suddenly and they have no time to react or save their property. So if the model is high resolution, it can resolve this thing. So it can, in the model, directly calculate the upflow, the downflow of this convection. So we call this explicit convection. But for the cost model, cost resolution model, say 100 kilometer, all of this is inside one box. So the model itself cannot even see such an event. And for this cost resolution model, these convection events, they are parameterized. So there is a numerical scheme that have some statistical, either statistical prediction or a sort of based on the stability to take out the rainfall based on some assumed stability profile, something like that. And then they put the rainfall down. So because the model cannot see this, so they generally do not produce correct rainfall because they don't, the event, the phenomena doesn't exist actually in the cost resolution. So that's what I was talking about. If the cost GCM cannot even, this phenomena doesn't exist in the cost GCM, and you downscale it, are you sure you can also produce what you want in the RCM? Yeah.
Okay. Yeah, I think it's very clear. Thank you for the answer. One person raised his hand. Please go ahead. Arif, Pak Arif, please go ahead, Pak.
Okay, thank you, Mr. Lee, for your presentation. I think the question is not so close with the presentation. Perhaps this question is a bit wide. How can we be sure that the regional model is accurate, considering the prediction time is 50 to 70 years? As you know, Indonesia has a complex climate system. Sometimes to predict on a monthly scale, the results are sometimes not accurate. What do you think are the fundamentals needed to build an accurate model, especially for marine intercontinental regions like Indonesia?
Yes. So this is the accuracy for climate model and accuracy for forecast model is slightly different. For forecast model, I think the key point is the easiest to solve point is actually better initial condition. And this is related to a better observation network. And this observation network, if it's better, will also provide better nudging for the forecast simulation. So for forecast, we want an accurate trajectory. So if we have good initial condition and we have good data assimilation to nudge the trajectory of the forecast, I think it will help more than spending a lot of time trying to work on the model. Of course, working on the model is important, but I do notice that assimilating good observation is the key point to a good forecast. For climate model, it is a sort of a different problem because it doesn't really care about initial condition. It actually cares about statistics. So it will actually, for ensemble run, start with many initial condition and there is no data nudging. So the idea is that if you have enough version of reality, so each run is a version of reality, or if you have a very long run, you have many repeated years. So on the whole, you hope that the statistic will be matching the statistic from observation. So maybe this is a more easy problem. And from a statistical point of view, you can also do some bias correction to match the model statistic with the observation statistic. So maybe in terms of global climate simulation is more rewarding than forecast to spend time improving the model. So I don't know if this answers your question, but for forecast, yeah, I know actually the tropical region is not so easy to forecast. But I think part of the problem, maybe our observation network is also not so good. So that may be a way, yeah, to improve the forecast.
Oh, okay, thank you, Mr. Lee.
Okay, thank you, Pak Arif. Any more question for Dr. Lee? You may raise your hand. I have one question, Dr. Lee. So
Yes.
your scaling factors, I try to understand that part. You did the scaling factors before you conduct those the verification with the distribution. So this is a scaling factor something like bias correction, or is it different thing?
It can be viewed as the same or different thing. So this work has been sent to reviewers and they have made some comments. So for if it's for rainfall, actually I think the scaling factor may not be needed because we know that the high resolution is better. So at the same time, the high resolution scaling factor is near to 1. So it's not needed actually, practically. For typhoon, is under review. And I think the scaling factor may also not be needed, although it is an attempt to make things comparable. Why it's not needed is because the cost resolution model, because ERA 5 that we calculate the scaling factor from is itself a high resolution global model, is 35 kilometers. So it actually it can create the real or similar to real tropical cyclone, and you calculate the scaling factor. And this is an assumption that this has been created. But when you take a cost, so you regrid ERA 5 to 1 degree, but the system still exists. So you can get a good scaling factor. But for the GCM at 1 degree, it doesn't have the system in the first place. So you cannot actually successfully apply the scaling factor to it. So I think in both cases, maybe the end result is you do need the scaling factor. But when we did it, we wanted to just make sure the spatial resolution was not causing some additional effects to bias our results. So we did this scaling or bias correction. But maybe in the end, it's not needed.
Okay, thank you, Mr. Lis. Maybe just a follow-up on that. You showed the scaling factor was calculated based on the gridded observation, so-called. What about the in situ observation, the point data? Is there any method to also perform scaling factor based on those point data records?
Yeah, so I have not tested it. I was going to, in response to the reviewers of my results, I was going to perform scaling to in situ results, the brain gauge, to see if it can also be scaled in the same way. I think it can be, because I compared the radar at the rain gauge grid, the radar grid point at the rain gauge, and their extreme rainfall results are quite similar. They should be, because the radar is also self-calibrated to rain gauge, right? So these are both observation-based and they should be similar. So in this case, the scaling factor should be able to work for the in situ too, but I haven't tested. But I think it can be, yeah.
Okay. Thank you, Ms. I looking forward for your publication, and I might want to use your scaling factor.
Yeah, thank you. I'm not sure if it will pass through the review, or I will remove scaling factor.
I will ask you directly then.
Okay, thank you.
Okay, anyone more questions for Dr. Lee? You may raise your hand or directly open your mic. Maybe one more for me. So Dr. Lee, the variable resolution simulation that you did for the tropical cyclone, I'm just trying to understand the technique, because you show the mesh grid, the changing resolution mesh grid, but in your analysis, you have different resolution from coarse resolution to high resolution, and I got the impression that you try to evaluate the same thing, right? But I thought those variable resolution, the one that are on the focus region is only the higher resolution.
Yes,
how
I
did
ran
you...
3 versions.
Okay.
I ran the no variable resolution, uniform all around. Then I run one more time, over the region is zoomed to 0.5. Then I run the third time, it zoomed to 0.25.
You have 3 simulation actually.
Yes,
with
I have
different
3
grids.
simulation. Yes.
Okay, I understand. I see. So how did is there any quick way to describe the technique of creating this mesh grid? Is it dependent on your focus region, or in the ocean model that you show, somehow seems the irregular grid can construct automatically, increasing their resolution closer to the coastlines for the ocean. Can we also do the same for the atmosphere? Let's say you have like a complex topography, then it automatically will sort of like increase the resolution by itself. How's the technique so far?
Yeah, so what I found out from trying to run these variable resolution models is that the most troublesome part is creating the variable resolution mesh. Then the rest is relatively straightforward, because sometimes if your mesh is not properly created, it goes from coarse to very fine too fast, or some other difficulties. The results may not be good. Of course, this is model dependent. Some models are more tolerant and some models are less tolerant, right? If you look at the NCAR, now they are working on this model called MPAS, which is the descendant, maybe it's a brother or younger brother of Wolf, and it has a variable resolution mesh. However, the ones that they provide, it is very smoothly decreasing, so it doesn't increase higher it's not more finer following topography. But theoretically, it is possible to do that. I think I have also seen some results of people who made meshes where at the mountain is where it's needed, they make the MPass mesh more high resolution. So it is possible, but to do it may be troublesome. So someone has to prepare this mesh using whatever method they have. Maybe they have to write their own tool. They have to write their own refinement criteria. Yeah. So this mesh creation is I think the major difficulty for us, for us as users of models, of these models. Yeah.
Okay. Just a quick check, because you also show the region where you increase the grid resolution for South China Sea, I guess, and it goes down all the way until the maritime continent. Does the resolution change as well for the maritime continent region? Let's say for the low level atmosphere, or it's just the same higher resolution with the one at the South China Sea, for example?
It's the same resolution. So actually, when we did it, because it was typhoon, for the tropical cyclone, we didn't, at first, we didn't want to include, or we didn't want to include maritime continent. The person helping me with the mesh creation, he's interested in tropical cyclone. Because if you include maritime continent, it will be more expensive. However, I persuaded him to extend to cover maritime continent. And I said, oh, you know, there's some research showing that MJO affects tropical cyclone, and so we also need the tropics. So in the end, it covers the whole face. So it should be 2.5 degrees, should also cover Indonesia. So if anyone interested to analyze, please try. But I cannot be sure if it will be good. Yeah.
Okay, thank you, Mr. Lee. Thank you so much for the answer. Okay, any questions? Maybe to Wendy also, to Pak Wendy, if you have question for Pak Wendy, you can use the forum, you can use the time. And maybe Pak Sulaiman have some question probably. We still have like 30 more minutes before 11 a.m. here. So maybe I will use time to off topic a little bit, Dr. because you show that you are involved in the second report, the Singapore government, the climate study for the second report and also the third report. I'm just wondering how do you compare the two? I mean, it seems that the third report that just got published last year, it has a higher resolution, 8 kilometers and 2 kilometers for the Sumatra. And they also use the variable resolution as well, the model, the SINV model. Can you tell us a bit, maybe your experience and how the work between the two projects?
Yeah. I can say actually these are both very big projects. So I was only involved in one area of the project. So I actually cannot tell you everything, because some people were running models, some people doing GCM selection, some people doing downscaling, some people, yeah. So it was a very big project with many people. overall, I would say for both of them, the most problematic part and most time-consuming part was to run the model, especially the downscaling. So version 2 downscale to, I think, is it 8 kilometers? I think 8 kilometers. And because it's done for Singapore, and Singapore is so small, it's only 10 grid points for the 8 kilometer regional model. So and even then, the downscaling took many people and a long time, very long time to run. It's like months and months, maybe 1 year of simulation. Version 3, third report, it downscale to, I think, 1.5 kilometer or 2 kilometer. And so it's better resolve the region, but even more expensive. So this was even more difficult computationally. First of all, the simulation itself is very difficult. It had to be run separately. It's too bad my colleague doing that is not here. Otherwise, he can tell you all the nightmare. So it had to be done on different supercomputer. And we also, I think, had to borrow some supercomputer from BOM. They help us to do it too, because there were not enough supercomputing resource. So we even have to borrow from BOM. And after the simulation, the data is so huge. Then how to move the data from one supercomputer to another, especially from BOM, Australia supercomputing to Singapore supercomputing, and how to manage all this data to one place to do calculation. So all this is what start me thinking about how to make efficient climate projection, how to decrease supercomputing resource, and how to make the data manageable, maybe selective simulation of extreme event, maybe not have high resolution everywhere. So these two projects, they may look different, but they are very similar in that so much time is and difficulty is actually spent on the simulation itself. So I think this is what I can tell you. The rest is, I think, relatively straightforward once you can get all the data together and compressed and manage. Yeah.
Okay, thank you, Dr. Lee. Just one thing I'm very curious. Looking at the increase of the resolution down to 2 kilometers, let's say, has there been any comparison done between the second project with the third project in terms of the performance? Is it really increasing between the second and the third? Have you seen any like those from our colleagues from CCRS done this comparison?
So when we were doing the third, there were plans to make a comparison, but I left before the project completed, and I'm not sure whether they have done the comparison. For the second, within the second itself, I would say the British, the Met Office scientists, especially the senior scientists, they are very scientifically rigorous people, and they are very accurate. So they did some experiments where I think they compared 12 kilometers. They have 8 kilometers, and they compared with, I think, is it 12 or 16? So they compared with a higher resolution, and they compared with they compared with coarser resolution, and they compared with finer. Finer is, I think, either 4 kilometer or 2 kilometer. I wouldn't be surprised if it's 4 kilometer, 8 kilometer, and 16 kilometer. So at that time, when using that version of the model, which is old version, long time ago, the reason why they did at 8 kilometer was not only because it was too expensive to do 4 kilometers. I think they found that the overall statistic was surprisingly better in 8 kilometers, I think. So they didn't just say, oh, we will do the highest resolution we can, but they actually test and say, oh, this is actually, for this version of the model, optimal to do at 8 kilometer. So they did comparison within the project itself, yeah. But not be too, but whether Met Survey Singapore did comparison for version 2 and version 3, which is old version of model and new version of model, I don't know.
I see. Okay. Thank you, Dr. Lee. So we still have plenty of times, 20 more minutes. Maybe Pak Wendy, you wanna share something?
Or maybe
Let's use the time for
Dr. Yuda, you can share something. Or we can end early.
Yeah, if there's no more question, maybe we can call it a day then. And thank you so much, Dr. Lee Xiaoyi from DPRI. Hopefully you can give us another talk. Probably you get a lot of interesting publication and some other topic, probably some other time. It's very welcome. So with this, then maybe I will invite Pak Sulaiman, our head of the research center. Maybe some closing remarks, probably, Pak Sulaiman. Is he still around? Hello, Pak Sulaiman. If not, then maybe, or Pak Wendy, wanna share something, or wanna
Yep,
use the time?
just
Probably?
one. Yeah, just I hope some days we can have collaboration with Dr. Lee to any kind research about the climate modeling in Indonesia, because Dr. Lee in actually previous institution before BRIN, we belong to Lapan. We developed the like WAF model, the maybe forecast model. Then I think yeah, it is also a good opportunity, I think, to use in the future. Whether I'm not sure how to correlate forecast model and climate model, atmospheric model. That's all I think, Pak Yuda. Just I do really hope to have collaboration with Dr. Lee in the future, since he's the one. I mean, I'm much excellent in this field. Thank you, Pak Yuda.
Okay, thank you, Pak Wendy. So Pak Wendy and Dr. Lee, you are not at the same office in Japan?
We are on the same floor,
Huh?
on the same corridor.
Neighborhood, just
neighborhood.
beside of my room.
Oh,
We are
okay.
different lab topics.
Okay.
Dr. Lee almost in like atmospheric circulation, and my lab is about hydrometeorological disaster. These are more related to the radar and short time.
Okay, awesome. Okay, thank you, Pak Wendy. Okay, back to what I just said previously. If there's no more question, then I think we can call it a day. Again, I invite Pak Sulaiman for some closing remark, probably. Since there's no more question, although still have 15 minutes. Maybe Pak Sulaiman is not on his place right now. So I think we can close the session. So thank you so much, Dr. Lee Xiaoyi.
Thank you. Thank you for
Uh,
inviting me to the talk.
My pleasure, Dr. Lee. And Pak Wendy, also thank you so much. All the participants, all the viewers in Zoom and YouTube.
Yes. Thank you, all the
And,
viewers. Happy
and-
holidays.
We are at the last week towards Hari Raya. So, minal aidin wal faizin, mohon maaf lahir batin. Hopefully we will meet again after the Hari Raya. And yeah, that's it. Thank you so much. And we end the event here. And we meet again maybe someday in the future, Mr. Lee. Have a nice day.
Thank
Thank
you,
you, Dr.
everyone.
Lee,
Makasih.
Pak Yuda.
Thank you, everybody.
Terima kasih Pak Wendy.
Thank you.
Terima kasih, Pak Yuda.
Terima kasih semuanya. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.
Bisa leave Zoom-nya. Terima kasih. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh.